Hello, my people. I hope we're doing well. Up to this point, in terms of our tests for convergence and divergence, we discussed in 11.3 the integral test, and in 11.4 the comparison test, both the direct comparison and the limit comparison. This section is actually kind of a nice pause because it's really easy, especially when you know that you need to be using it, and you always do. This is basically the test. This is alternating series, the test for convergence for alternating series, and sort of a little bit of error calculation when you approximate a alternating series. So an alternating series is anything that goes positive, negative, positive, negative, positive, negative, positive, negative. The one that we're most familiar with, the one that we've already seen, is the alternating harmonic, right? The harmonic series is 1 plus 1/2 plus 1/3 plus 1/4. It is the series that includes all of the unit fractions. But an alternating harmonic series has all the unit fractions, but the sign flips back and forth between positive and negative. Now this impacts its convergence, okay? It is not divergent, but convergent, and you can sort of see that from this visual proof right here. And the visual proof is basically, if you start at 0, that first 1 is going to take you out to here. And then you need to subtract 1/2, which is always, of course, less. And then you need to add 1/3 and subtract 1/4, and then add 1/5, and then subtract 1/6, and then add 1/7, and subtract 1/8. And what you're doing is you're slowly but surely arriving at this sum right here. It basically is pushing in from both sides to arrive at that sum. And that would basically just be the visual proof that the alternating harmonic series is actually convergent. Now we can sort of basically extrapolate that out, abstract that to any alternating series, but of course the alternating series which we are discussing, it has to be true that each term is less than or equal to the original term, okay? Basically, and it's basically less than, and basically what happens is each motion back and forth has to be a shorter distance in order to be sort of honing in on this sum right here that exists kind of right there in the middle. But of course, it's not only the fact that each term has to be less than the preceding one, it's also that those sums actually have to be going towards 0, okay? So if you're dealing with an alternating test, an alternating series, the test for convergence is that B sub n, and let me zoom in just a little bit so this is easier to see. That B sub n right there, and B sub n does not include the -1 to the n minus 1 or -1 to the n, whatever's there generating the positive and negative flip-flopping back and forth. That B sub n is each successive term smaller than the first one. Okay, that would logically should make sense to you, so I'm not going to labor that point. But of course, not only is it smaller, but each successive term needs to be going towards 0. So the limit as n goes to infinity of B sub n is 0, and that makes sense. If each successive term was smaller than the one before it, but each successive term was going towards 1, then no matter how many terms you go out, you're still adding 1 and a little something, 1 and a little something, and that obviously is not the recipe for a convergent infinite series. So there are two criteria that have to be met. One is that you need to basically demonstrate that each successive term, or the next term, meaning B sub n plus 1, is smaller than or equal to B sub n, and the fact that those B sub n values, as n goes off to infinity, are approaching 0. Alrighty, so let's do some example problems. Now, if we, actually, I'm going to zoom back in. I think it's, since we're only going to be taking up half of the sheet of paper each time. Now, remember that your B sub n does not include that right there. That's kind of the point, right? So your b sub n is basically the absolute value of your a sub n. So what we're going to do here is my b sub n is 1 over the natural log of n plus 4. My b sub n plus 1 is 1 over the natural log of n plus 5. Now, natural log slows things down, but is n plus 5 larger than n plus 4? And the answer is yes. So is the natural log of n plus 5 larger than n plus 4, natural log of n plus 4? And the answer again is yes. So if this denominator is always larger, then this quantity is always smaller, and you have confirmed at least that part of it. Now, the limit as n approaches infinity of b sub n is the limit as n approaches infinity of 1 over the natural log of n plus 4. And like I've said before, natural log slows things down, but natural log is an always increasing function on its entire domain, and therefore this gets really, really large without bound, and 1 over really, really large without bound is always 0. And both of those check off, and therefore it is convergent by alternating series test. Okay, let's do another one. Again, remember that when you're dealing with your b sub n, that right there, that sort of alternating series, that the thing that basically sets alternating series apart from just regular series, is not included in your b sub n. So this right here winds up being n to the 1/2 over 2n plus 3, and this becomes n plus 1 to the 1/2 over 2n plus 5, right? After you distribute the 2 and simplify that denominator. Now remember that each successive n value is only going to increase a little bit in the numerator, but much more in the denominator, right? Because each successive n value, so difference between 2 and 3, square root of 2 and the square root of 3 is an increase from 1.414 to 1.732 in the numerator. But in the denominator, it's an increase of, you go from 2 to 3, and you're going to go from, you plug in 2, and you're going to get 2 times 2, and that's 7. You plug in over here, and it's going to be 14. Or, I mean, it's going to be, sorry. Oh, doing arithmetic in my head when I'm trying to speak. Remember that this came from that, right? So if I plug in the next number here, it's going to be 2 times 3, which is 6 and 9. So basically, the numerator increases a little bit. The denominator will always increase more. So if the denominator is always increasing more, then each successive term will always be less than. So that checks off. And of course, we've done this kind of limit before. This becomes n to the 1/2 over 2n plus 3. Now, if we wanted to do it, if we wanted to be real sticklers about this, we would, of course, do it by limits at infinity, and we would go ahead and we would get 1 over n to the 1/2, 2 plus 3 over n, and that's going to be 0 over 2, or 0. The limit goes to 0 for, as n goes to infinity, of that b sub n. Both of the conditions check off, so it is convergent. Alrighty, let's do another one. So we have the sum from 1 to infinity of -1 to the n minus 1, and again, I'm going to remind you that this is not part of our b sub n. Okay, our b sub n is arctan of n, and so b sub n plus 1 is arctan of n plus 1. Guess what? Arctan of n plus 1 is always greater than. Think about the graph of arctan. It has an upper bound because it has that horizontal asymptote at y is equal to pi over 2, but it is always increasing toward it. and therefore each successive x value, or in this case each successive n value, will bring you closer and closer and closer to that pi over 2, but it still winds up being larger than the preceding term. Okay, so that does not work. Now, we also can tell that from the limit as n goes to infinity of arctan of n, what happens here is this goes to pi over 2. And so, especially as you get to really, really, really large values of n, functionally you're adding pi over 2 each successive n value, or something just negligibly different from pi over 2. And that's certainly not a recipe for a convergent series. So it fails both of those, not that you had to check both, and therefore it is divergent. Now, this one winds up being a little confusing because sometimes when we have that like pi over n or something squirrely like that in the angle measurement expression, we sometimes kind of have a little hiccup, right? So let's just talk about it. Okay, now our b sub n is cosine of pi over n. This is going to be cosine of pi over n plus 1. Okay, I'll tell you what. Let's ignore the negative 1 to the n for a second, and let's actually just list out, let's go ahead and just list out n is equal to 1 to infinity of cosine of pi over n. Okay, let's just ignore it because what we're looking for, we're gonna need to basically evaluate regardless of the negative 1 to the n, right? Just b sub n. So if we do that, this becomes cosine of pi plus cosine of pi over 2 plus cosine of pi over 3 plus cosine of pi over 4 plus cosine of pi over 5 plus, cosine of pi over 100, right? Okay, cosine of pi over 100 is getting really close to cosine of 0. So if each successive term is going off closer and closer to cosine of 0, that means that basically if you think about the unit circle and these values on the unit circle, what's going on is you start off here and basically you're sending off going that way around the circle. But remember, when you're dealing with cosine, you're dealing with the x measurement. So really, cosine of pi starts off at 0, or basically cosine of pi starts off here at negative 1. Cosine of pi is 0, but then basically it winds up going just closer and closer and closer and closer and closer to here. So basically after the pi over 2, for all of these terms, you are adding values that are greater and greater and greater and greater and greater because they're going towards 1. So that means that it is, basically this is always less than that. And even if you didn't see that, you could show that cosine of pi over n is equal to 1. And it therefore fails on both accounts. It is a divergent series. All right. This really just winds up being a nice little reprieve from sort of the difficulties that came beforehand, okay, in the prior sections. Not that they were all that difficult, but when it comes to basically when you get to a test or a quiz and you see an alternating series, you almost breathe a sigh of relief because there's not a whole lot of ambiguity that goes on there. Okay. Now, let's entertain the question a little bit differently. It said, for the following series, what values of p give me a convergent series? Okay. Well, remember that the test stipulates that my b sub n needs to be greater than my b sub n plus 1, or it needs to be greater than or equal to. Okay. Alrighty. Well, what that means is my 1 over n to the p needs to be greater than or equal to 1 over n plus 1 to the p. Now, for what values of P, is that true? Okay. Well, basically, you know, that's the same thing as asking this question, right? Because when 1 over n to the p is greater than or equal to 1 over n plus 1 to the p, it's going to be the opposite relationship for their reciprocals. Okay, so when is that true? Well, I got news for you. That is only true for positive values of p. Okay, well, let's go ahead and let's look at the limit as well. So if we have the limit as n approaches infinity of 1 over n to the p, and we want to know when that goes to 0, so for what values of p is that true? Again, it is for the positive values of p. And here's how we sort of reason that out in the negative. So for values of p equal to 0, okay, basically what happens is n goes to the 0 power, which is 1, and basically that transforms this series into just -1 to the n minus 1, which basically means 1 minus 1 plus 1 minus 1 plus 1 minus 1 all the way up, okay? Now, you know, there's an occasional mathematician that will tell you that that actually does have a sum. But most mathematicians and most textbooks basically tell you that if it just goes back and forth between 1 and -1, then what happens is each partial sum right here winds up being 1, 0, 1, 0, 1, 0. So I think Euler was one of those squirrely mathematicians. I think he said, yeah, definitely, the sum is 1/2. Because he basically just split the difference between what happens to the partial sum after each term. But most mathematicians don't follow along in that. And, you know, Euler, as brilliant as he was, can, of course, be, you know, kind of weird and wrong at times. But what about values of p that are less than 0? Well, if p is less than 0, then you have n to a negative exponent, and that negative exponent, that basically then into the p gets sent to the numerator, okay, with a positive exponent, which means that the limit as n approaches infinity of 1 over n to the p is equal to infinity, because, you know, for example, if you have the limit as n goes to infinity of 1 over n to the -1/2, that becomes the limit as n goes to infinity of n to the 1/2, and that's always increasing and therefore infinity. So that's just an example. Okay, so e.g. Alrighty, let's go ahead and look at one more problem before we discuss alternating series, their approximation, and how we can calculate the error for those approximations. Let's say that we are given the series -1 to the n minus 1 b sub n, where b sub n is 1 over n if n is odd. So the odd terms in the series wind up looking like 1 over n, and b sub n is equal to 1 over n squared if n is even. Okay? Show that the series is divergent. Okay? Now, why does the alternating series not apply? So 2 parts. But let's go ahead first and actually show what this looks like. Okay? So n is equal to 1 to infinity of -1 to the n minus 1 b sub n. And each odd term, and maybe I should do these in different colors. I don't know. Let's just go with black. You know that the first term, n is equal to 1, -1 to the 0. So the first term is going to be positive. Yeah, that's all you have to determine, and then you just know that they change sign each time. So you have 1 over 1 minus 1 over, But this is an even term, so that it's going to be, the denominator is going to be squared, 2 squared, or 4, plus 1 over 3 minus 1 over 4 squared, plus 1 over 5 minus 1 over 6 squared, plus dot, 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 right? So really, you actually could take these and split them up, right? You could, these are the 1 over n's, okay? And these are the 1 over n squareds. And so you could actually split this up into 1 over 1 plus 1 over 3 plus 1 over 5 plus dot, 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 minus, and you actually could factor out a 1/4 if you wanted to, but I'm not going to, 1/4 plus 1/16 plus 1/36 plus dot, 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 dot. And that's what it looks like, right? If you actually split it up, because really two things are going on. So this actually does wind up being the sum of two different series. So you could actually represent it as 1 over 2n minus 1 minus, okay, 1 over 2n squared. Well, I got news for you. This right here is divergent, and you can basically show that because it's comparable to the harmonic series, and because it's comparable to the harmonic series, you can demonstrate that it's going to be divergent as well. This right here is a p-series. It is convergent. Now, things are divergent because they're infinite, right? Things are convergent because they're finite. Infinite minus finite is, like, it's not even indeterminate. It's still infinite, okay? And therefore, if it's still infinite, it's still divergent, okay? It doesn't matter how big this finite number is, it will pale in comparison to the infinite sum here, and will not take, it will, not take anything away from its divergence, okay? So this is divergent, okay? Now the next part of the question is, why does the alternating series test not apply here? Well, just look at each successive term, okay? In order for each successive term, especially if you have a common numerator, right? 1, 1, 1, 1, 1, 1, 1. In order for each successive term to be less than the term before it, it has to have a larger denominator. So in order for the alternating series test to apply, you should get a larger denominator in each successive term, and you don't, right? 1 to 4, it goes larger, smaller, larger, smaller, larger, smaller, and on and on and on. And that's the way it'll go for the whole thing. So because it fails, right, alternating series test fails because, basically b sub n plus 1 needs to be less than or equal to b sub n, and that is not the case. Okay? And so basically it fails that one component of the alternating series, and therefore it fails the whole thing. Now, could you actually wind up representing this series as a single series? Yeah, and we can play around with that for a second, but I'm just going to go ahead and tell you that you don't want to. At least not on your own, but you can watch me. All right. All right. So we have, again, n is equal to 1 to infinity of negative 1 to the n minus 1, b sub n, and that's positive 1 over 1, minus 1 over 4, positive 1 over 3, minus 1 over 16, positive 1 over 5, minus 1 over 6 squared, or 36, and on and on and on and on and on, right? So here's the thing. This first term right here, right, is 1 over n for that particular n. this winds up being 1 over n squared. Negative, right? And then again, 1 over n, and then negative 1 over n squared. So you know how to basically make it go back and forth between 1 and negative 1, and in fact that's even taken care of for you. But how do you make the n, that extra n, disappear in each odd term? Well, you have to basically play around with powers, right? And so basically what happens is you need to basically just focus on what happens to the powers. This winds up being positive 1 over 1 to the first minus 1 over 2 squared plus 1 over 3 to the first minus 1 over 4 squared plus 1 over 5 to the first minus 1 over 6 squared. So I guess what you're really asking yourself is a related question on a series. How do you make a sequence or a series go, how do you go 1, 2, 1, 2, 1, 2, 1, 2? Well, there's a couple ways to do it. One of them is the fact that you can think of 1 and 2 and think of what's in the middle. It's 3 halves, right? So this first one is 3 halves minus 1 half. This is 3 halves plus 1 half. This is 3 halves minus 1 half. This is 3 halves plus 1 halves, and on and on and on and on and on. But that's going on in the numerator, right? So what needs to happen here is obviously this becomes 3 halves plus a negative 1 to the, let's say n times 1 half, right? Or think about it as 3 plus a negative 1 to the n over 2. Now, all of that right there is basically creating these exponents right here. And so what this really looks like in terms of an actual sigma notation is n is equal to 1 to infinity. And of course we need the original back and forth alternating generator. And this 2 right here, I don't want to put that in the exponents. What I'm going to do is I'm instead going to bring it down, and instead of calling it 1 over n, I'm going to call it 1 over the square root of n, and then raise that to the 3 plus negative 1 to the n power. Okay? And therefore, every time, like when you plug in the first one, that's going to be 3 minus 1, or 2. Now that squaring is going to cancel with that square rooting down here, and that's going to cause it to be 1 over n. But when I plug in 2, that's going to be 3 plus 1, or 4. Now it's going to be 1 over n to the 1 half times 4, or 1 over n squared, and that's going to take care of it. Now you could also use trig, but it would be something really nasty like, let's do negative 1 to the n minus 1, and then we have 1 over n, and then we'll let this next 1 over n, we'll try to make it disappear, so we'll do cosine of pi over 2 n minus 1 squared, right? Because cosine squared is going to oscillate between 0 and 1, and what you're doing is you're just transforming it such that you're hitting the zeros and the ones at basically your natural numbers, and that sort of is equivalent to that. Now, of course, this one right here winds up being much easier, but neither of them are fun. And if I ever gave you something like that, it of course would be I would never give you something like that as part of the test except as an extra credit problem. Not because I don't want you to work through things like that and have puzzles like that, but on a test or a quiz, I don't want a problem like that to suck up unnecessary time and energy away from what I'm trying to assess. I hope that is helpful. If you have any questions, do shoot me an email. Bye.